Hello everyone. Welcome to the 8th International Conference for Convergence in Technology. My name is Robi Pal and I will be presenting my research on design and performance investigation of silicon germanium heterojunction based vertical dual pocket biosensor design based on charged plasma TFET. So without any further delay, I will be starting my presentation. Let us see what to expect in this presentation in a chronological order. Firstly, we will be seeing an introduction of our device. Then see the device parameters and considerations. Have a brief analysis of the performance aspects of the device. Here, we have considered alteration of dielectric constants of the biomolecules that will be accumulated in the pocket region. Also, we have considered charge density situation and also the field factor variations. Then we have also done sensitivity analysis of the device to finally determine the performance aspects. And after all this, finally we came to a conclusion. So what will be the key aspects of this research? As the device is based on TFET design, to improve the on-state current, is silicon germanium heterojunction is implemented to improve the tunneling of the carriers. Introduction of an additional pocket region in the source side helps to allocate higher amount of biomolecules, which helps in the sensitivity analysis of the analysis and also subthreshold sensitivity of the device. The vertical design of the sensor helps easier implementation in the CMOS technology, leading up to array designs. The implementation of charged plasma technique nullifies problems like random doping profiles and also reduces complexities in the fabrication stage. Here we see two tables. The left orange table represents the specifications of the proposed vertical dual pocket design, and the other shows considered biomolecules with dielectric values. The structural parameters are kept constant throughout the study, where the dielectric constants are changed according to the needs. As the name of this research suggests, the focus of this study was to investigate the performance of the device in different areas to determine the significance of the device. Initially, the device is simulated altering the dielectric constant of the device and charge densities. Then the device is tested having different field factor variations, keeping neutral cases in mind. Finally, the sensitivity analysis also shows the desired sensor results. When the molecule enters the pocket region, the permittivity of the area starts to change, affecting the device's electrical properties. This affects the device's performance compared to usual situations in which the pocket area is assumed to be empty with a dielectric constant value of k is equal to 1. Here, this figure shows the subtle variations of electrical properties caused by the presence of biomolecules. Figure A and B depict the effect of various biomolecules on the device's transfer and output properties. Through C and D, we can witness the impact of dielectric modulation on the device's energy band and surface potential. As the dielectric constant value rises, the energy band bending at the junction becomes more noticeable. This results in a greater number of carriers to tunnel through, which eventually increases the ion current. The impact of the dielectric modulation on the subthreshold swing, tunneling rate, and ion-off ratio is shown through figure E and F. Due to the enhanced gate control, an increased K yields a better subthreshold swing value and thus a substantial ion-off ratio. As biomolecules that are available in the nature are to be either positively and negatively charged, and such areas are also need to be considered. Here, the equation displays the effect of charged molecules in the pocket region of the TFET device. Whenever the pocket area is infiltrated by positively charged molecules, it raises the density, increasing the third portion of the equation. To counteract the increment, the surface potential is also needed to increase. Again, whenever the region is infiltrated by negatively charged molecules, increasing the density will decrease the third subpart of the equation, which needs to be handled by reducing the surface potential. Here, the figures on the top and bottom shows the effect of positively and negatively charged biomolecules present in the pocket region respectively. As shown, as we know, increasing the surface potential value improves the tunneling process, the drain current, electron tunneling rate, and ion-off ratio all tend to increase for the positively charged cases. Again, due to alternative, all tends to decrease for negative cases. The fill factor, normally indicated by the amount of the region to be filled by infiltrated biomolecules and profiles, describes how it is filled. As such, it is an essential factor for determining the performance aspects of the biomolecule design. Here, the two figures on the top shows a partial but uniformly filled case where the biomolecules are filled in one side, and the other shows the fully filled case. The figure in the bottom side shows the effects of fill factor variation on the transfer characteristics, subthreshold swing, and ion-off ratio. We can see that as the fill factor raises, the biomolecules are more subjected to phase alteration of its electrical properties due to the biomolecules present, improving the performance of the every aspects. Despite the consideration of uniform cases, the non-uniform accumulation of the biomolecules is more likely to occur in the natural settings. We also need to investigate these possibilities to properly scrutinize the proposed device's performance aspects. This manuscript considers 4 possible profiles for feasible non-uniform cases that can occur naturally. These profiles are visually demonstrated through figure A and D. Due to their accumulation nature, the increasing and concave profiles hold the maximum amount of molecules near the gate junction compared to other two cases. As the amount of biomolecules influences the tunneling barrier to reduce, a significant drain current will be found for the increasing profile than the concave profile. The convex and the decreasing setting will have the representative drain current amounts. Here the decreasing contains at least as from the illustrator profile of E, as the maximum amount of biomolecules is accumulated farthest from the source channel junction, having less influence over the tunneling barrier. Due to such, the ion-off ratio is influenced having the increasing profile, the maximum ratio and decreasing having the least. Sensitivity is a crucial factor that influences the overall effectiveness of the biosensor device. Here, figure A depicts the dielectric modulation impact on the device's sensitivity under neutral circumstances. The constant K lowers the tunneling barrier, increasing the drain current and enhancing the device's sensitivity. Considering the pocket region to having 100% fill factor, the proposed biosensor design exhibits higher sensitivity values with increasing dielectric constant as a higher amount of molecules is present in the pocket. However, the introduction of charge density begins to affect the device's performance expectations. The increase in positive charge in the pocket accumulates the carrier tunneling by enhancing the surface potential. In constant, increasing the negative charge of the molecules decreases the tunneling operation by raising the tunneling barrier and decreasing the device's sensitivity relative to neutral conditions. Figure B and C illustrate the effects of influencing charge density over the device's sensitivity value. In positive cases, the sensitivity increase as the device value decreases. In contrast, negative density values are decreasing due to the density increase. Here, the table illustrates the findings of the sensitivity analysis related to observed non-uniform profiles. Given the accumulation of molecules near the junction area, the increased profile displays the maximum sensitivity under all considerations. Due to a pattern of molecule accumulation, the concave profile has the following sensitivity value, whereas the convex and the decreasing profile provide lower readings due to the molecules accumulation patterns. Then, with increasing positive densities, the biosensor demonstrates an increased sensitivity while decreasing trend for the negative cases. Here, the figure illustrates the relationship between the maximum drain current sensitivity and the subthreshold sensitivity for positive, neutral, and negative charge densities versus the dielectric modulation when the constant drain and gate voltages are applied. As dielectric constant value rises, the drain current and the subthreshold value sensitivity increase for all charge densities. The proposed device design yields a maximum sensitivity value of 7 into 7.78 into 10 to the power 8 for neutrally charged cases when DNA is present in the pocket region. Again, considering the positively charged biomolecules, the sensitivity value rises to 3.50 into 10 to the power 9 for DNA, which reduces to 1.29 into 10 to the power 8 for negative cases. Furthermore, the figure showing the subthreshold sensitivity also justifies the previous observations. As the dielectric constant K rises, so does the sensor sensitivity, which also suggests that the sensor is more likely to detect the molecules more accurately, increasing the subthreshold sensitivity value. The highest subthreshold sensitivity value for our proposed device was achieved during the dielectric constant value being K is equal to 8.7, which is for DNA for all charge density profiles. While the positive being the highest, the negative profiles are the least for each of them. So at the end, what we can say that due to being based on TFET design, the biosensor contains a lower off current and also achieves a higher on current due to the silicon germanium heterojunction. The implementation of charge plasma technique nullifies problems like random doping profiles and also reduces complexities in the fabrication stage. The use of the dual pocket design yielded a higher value of sensitivity at the same technological node. When the neutrally charged DNA is present in the pocket region, the value of sensitivity was 7.78 into 10 to the power 8, and the sensitivity rises to 3.50 into 10 to the power 9 during the positively charged cases and lowers down to 1.29 into 10 to the power 8 for negative. I have reached the end of my presentation. Thanks to all for your kind attention. If you have any questions, you are welcome to ask. Stop share.